He's going to speak about climatology and hydrology.
Good evening, everybody. It's been a long day, but I promise there'll be no questions, so it'll be a bit easy on all of us. So, there's a lot of pretty pictures. So, something completely different. So, first off, I want to thank the organizers for inviting me. It's a great honor for me. I've been a friend of math science for more than 20 years now. My cousin works there in the theoretical science department, in 1991, he came back from Canada and joined the institute. That's when I was even aware of the institute, and that was the year when I left for the US. And since then, every time I come, I visit math science, and I know several of you. Initial years, there was not much of activity beyond the sort of the traditional areas, but then over the last few years, there's a lot of interest in diverse topics, and I was happy to give 2 or 3 talks in the last few years. So I hope this continues, and I'm really happy for the opportunity and also to share some. Yeah. Okay, so with that, I want to acknowledge my co-authors and collaborators, co-conspirators on the talks that the 3 talks, the results, and things I'll be presenting. And also funding for much of this work from these agencies. So this is going to be broad outline, and I'll continue as long as time permits, and then I'll take over in the second and third lectures. So what I'm going to give you is a little brief overview. So this talk today is not going to be proper Bayesian per se. I'm just going to set the problems, because I'm guessing not many of you are aware of what are the larger issues in this area. So I'm going to take the time and provide you with sort of the context, the problems, and the issues. And along the way, I'm going to point out what kind of Bayesian methods people have used, we have used, and then I'll come back to it in second and third talks to sort of close the loop. So these are some of the problems. They're not exhaustive, but sort of leading problems that people face in this field, seasonal forecasting. So I'm going to give a little premise on that, sort of a climatology 101. Then stochastic simulation, some extreme value analysis problems, failure reconstructions, and then, as I said, I'll point to Bayesian applications, setting up the stage for the second 2 talks. Human beings have always been fascinated with forecasting. So forecasting everything from personal lives to all sorts of things. And this is a quote from Genesis, which sort of speaks to that aspiration, mentioning 7 years drought. So what gives that predictability of that 7 years, or anything beyond? I mean, it's hard to comprehend in a system like climate and weather, where all you see is just chaos and noise. And what I will point out is that there is some order in this madness that people have harnessed for skillful predictions. So when you talk of climate variability and predictability, this is sort of how I envision. This is the time scales over which you're interested in, and these are the processes over which processes that operate on these time scales. The first 2 I put here, daily and annual. These processes are very well known, sort of boring. There's nothing to predict per se. Although day-to-day weather is a different story, I'll get to that. This is where the interesting part is, the interannual to interdecadal. And what separates this from this is it is quasi-periodic. So life is not perfect like here. There's no diurnal cycle, day and night, spring following winter, and so forth. And that's what is fascinating. And that's where a lot of the findings, the research that led to the current state of predictions that we have in terms of seasonal predictability and weather. And these are some of the processes I'll sort of quickly go through. And then this very long time scale, centennial and millennial, again, there are processes, but then this is timescales beyond that.
Meanwhile, what is thermohaline?
That's a thermohaline circulation. So thermohaline is it's the process in the ocean where thermohaline circulation. So it's a process in the ocean where in the Atlantic, where heat is transported from the equator to poles, and the Gulf Stream, which is one of the notable feature in the Atlantic Ocean, transports this warm water from the equator to the poles, and that conveyor belt is critical for the climate, and also particularly, as I say, for the undeservingly warm weather that England enjoys, sitting in 60-degree latitudes. So that is the thermohaline circulation, and that operates on a 100-year time scale. Roughly, that's the periodicity of that process. And there's also a lot of links to that cycle to global climate. And then Milankovitch is more for the geologists. It's more sort of thousands of years time scale. Again, this scale is not terribly useful. I mean, it's interesting, but something that we can't comprehend in terms of if you want to make decisions, this is where the action is. So again, when you talk of climate and weather, there's a famous quote by Ed Lorenz who said, "Climate is what you expect and weather is what you get." So this implicit in this is climate is the expectation of this sort of random process. So which means when we say climate prediction, it is the statistics that we are predicting. And I'll come back to that, and I'll hit that point again. And the weather is more of, well, what's going to be tomorrow's weather, or today's weather, afternoon's weather, and so forth. The weather forecast is typically, is it raining, no rain, what's the temperature going to be. So a little bit more clarity in terms of the variables. Whereas the climate forecast is more probabilistic, because obviously you cannot predict the entire season, daily weather over the entire season, but then you can predict the statistics. And this is something people always have difficulty in whenever you're in parties or somewhere talking to people. Like, how can you cannot predict tomorrow's weather accurately? How can you predict season? This is bogus. And then particularly the climate skeptics then say, well, if you can't predict weather, what can we? How do we believe what's being projected 100 years from now? So what needs to be separated in our minds is when we talk about these long time scales, we are talking about the statistics. We're talking about the distribution, probability, the mean, variance. Whereas when you're talking about weather, it's much more day to day. And that statistics is predictable is what I will submit to you. Okay, so forecasting of our time scale, lead time, and the processes. So, yeah.
Lorenz, you mentioned Lorenz. Is it the same Lorenz of the Lorenz curve?
Yes, the butterfly.
No, there was a population person.
No, this one is
income inequalities.
No, this one is Ed Lorenz from MIT. He was the one who found chaos.
This is
it's the butterfly chaos person. So again, this is sort of the time scales. You have very short time, 6 to 10 days. That's sort of the weather time scale, and then all the way up to season, and then going beyond several years, multiple years. So again, in forecasting, these are sort of important, and processes I mentioned about. So large, sort of two broad things that drive climatology, two broad circulation. And one of the circulation that is of critical importance is this Walker circulation. It's the same Walker, by the way, that was the statistician Yule Walker fame. So, and it's an interesting story about him that he was the first person to identify relationships, correlations between pressures variations over Australia and the Indian monsoon. And he reported that, and he was the first pioneer of interdisciplinary research. And he was criticized and sort of shunned in both the fields. The statisticians thought he was not a statistician, whereas he was identifying all these things. The Walker equations, which is used these days, as someone pointed out, in cell phones and all the other technology. He also pioneered findings in meteorology, introduced application of statistics in meteorology. And the meteorologists didn't think much of him because they thought he was a statistician masquerading as meteorologist. And he got all the awards and recognition posthumously. And in fact, some of his insights were so good from his findings from applying data to these processes. And he was, by the way, the Queen's representative to India. And his charge was to understand and predict the monsoon, because the British were occupying, that was very important for them. And he's also the father of the Indian Met Department. So there's a Walker lecture and award after him. So.
When was this?
1920s. So there's a seminal paper which is widely quoted. In fact, unlike somebody pointed out, Bayes' paper, his is quoted quite a bit, even to this day. So, anyway, simply put, what Walker's circulation says is that this is the equator where the sun belts all the time, so it's hot, there's convection, air rises, and when air rises, it has to sink. As it goes up, it cools, it gets heavy, and then it sinks. Where it sinks, it's high pressure, it suppresses convection. Where it rises, there is convection, there's going to be more rain. That's sort of the simple. And this is where the sinking and rising, and in fact, if you take the globe and look at generally where places are nice and warm and dry are places where typically you have this kind of sinking motion laterally along the longitudes. So this is the Walker circulation. The other most important is the Hadley circulation. And these two sort of what forms the planet, sort of the broad features. The Hadley circulation is exactly the same but poleward. So you have air rising at the equator, then it starts sinking at the poles. So this circulation here is Hadley. Circulation that occurs on the, along the longitudes is the Walker circulation. And these circulations are what causes winds, jet streams, monsoons, and then that is what you then use to make your predictions. The oceans play a critical role here, and what you're seeing here, for example, in the equator, you have trade winds. So we go from Geography 101. Trade winds go from east to west, so they pile up all the warm water. That's why water is warm here. Convection, and you have these gradients. So you have these gradients that are set up in the oceans by the winds, and those coupling of the ocean and the atmosphere, which then produces these circulations, which then brings weather all over the planet. So at the first cut, you can see that there is some organization to this madness. But also at the same time, see the word teleconnection. And Walker was the first to point that out. The teleconnection simply says that there are certain processes that happen here, which are then teleconnected to something that happens here. Because there are teleconnections, immediately you go to probability. Because they are not connection, they are not direct connection. So sometimes they are, sometimes they are not.
How steady are these cycles?
These are climatology, so these are fixed, no problem there. Okay, so that's why on an average, if you go to Singapore, Malaysia, it's always hot, humid, muggy, green, wet, because of this phenomenon. Now what happens occasionally, these climatological features get disturbed. And when they get disturbed, you can imagine if think of it as a game, I just pull this thing here. So I pull the convection here, so that means I'm taking this subsidence and putting it here. This subsidence goes over there. So in other words, as I change these things, immediately you can intuitively see the weather changes. And what causes those changes, and they are not periodic. That's what back to my modes, which are aperiodic, unlike seasonal cycle. These changing of these, pulling of these warm and cold centers happens once in a while. And that prediction is very, very important to then being able to project those process predictions or changes to weather and climate in different parts of the world.
I'm sorry if I missed this and you said this, but the rotational symmetry breaking of where this is that because of the land?
Yes.
Sea?
Yes. So there is land-ocean and also land-ocean contrast. So, for example, if you get to Indian Ocean, there's other processes that come into play. If you get to the Atlantic, which is a smaller basin relative to Pacific, it has a different. But there are some broad climatological features that are same all across. And where these things rise and subside are fairly well known. In fact, as I said, in the subtropic, in the Hadley zone, for example, where it sinks, it sinks around 25 to 30 degree latitudes. So that's why if you take a globe and see, all places around that are usually warm, nice, sunny places. So that is what we call climatology. So that is sort of what you would expect on an average. But year to year, things change. Yeah.
How often does it change?
And that's where been the most area of active research over the last decades. And what changes? So again, this is yeah.
It's two questions. One is, so once it changes, what's the time scale of recovery?
So the process, this change here itself is about 18 months total. So think of it as a pendulum. So this is the normal state. So you disturb the pendulum, so it goes to the other side and comes to the middle. So that takes about 18 months roughly. And it happens every 2 to 3 years sometimes, and sometimes it happens every 3 to 8 years. So there have been epochs where it never happened for 20, 30 years in the middle of the 20th century. And in recent decades, it's been happening every 2 to 3 years. And whenever this happens, it not only affects this, but it also affects this. So which means you're affecting the weather all over.
And the second question is, so in the Hadley circulation, there's the warm current, the red is warm, right?
Red is, these are the winds.
Yeah. So there's, they go in different directions at some.
Here?
No,
Here.
at the tropic of Cancer.
Yes, that's due to Coriolis. So that's why in the mid-latitudes, the prevailing average wind is westerlies. So that's why in the tropics, the prevailing wind is the trade winds east to west.
But you would expect Coriolis to be across the equator.
Yeah, so when you get out of the equator, it moves things to the right. So as you go higher and higher, it keeps moving to the right and right, and you end up with that. Okay, so this is the monsoon picture, and I won't get into this. So this is the teleconnections you can think of whenever you're changing the warm waters. So you're actually triggering waves in the atmosphere, which then leads to this kind of pattern. So when if you're in North America, you get this jet stream, which is essentially what brings the weather in the winter time. And there's a similar behavior in the southern hemisphere as well. So these are called teleconnections. So depending on where this heating goes, the strength and the location of these waves change, and correspondingly the winds or the jet stream changes, which means the storm tracks change, the weather changes. What is nice here is that intuitively, conceptually, it's very clean. Yeah, you change the heating, but the problem is when you change this, what happens here has to come through the atmosphere, which is chaotic, and that is where the probability comes in. And that's why forecasting and information provided is all probabilistic, because you know the physics, it's pretty good, but then what you get is could be anything. Yeah, there's a expected value, and then there's also things. Many times things don't just happen the way it should. So in other words, if you're closer to this action, the connections are much more immediate. So you're much more certain. As you get away from the action, it's a lot more diffused, and there's other processes that can contaminate the same. So this is what that process is called, El Nino. I'm sure a lot of you must have heard and read a lot about it. And this is a coupled phenomenon. I won't go into the details, but this is what pushes the convection back and forth in the equator, and this happens on a cycle that goes from 3 to 8 years. These are the teleconnection patterns when it happens. This is how you can see the effects all over the world during the summertime and during the winter time. So this is what is used to predict. And over the years, there's been a lot of efforts put into monitoring, and so monitoring the ocean and atmosphere in the Pacific. And you can go to a website, pnel.com, it's a NOAA lab. You can get real-time sea surface temperatures and so forth, which are then used in these models to predict whether it's going to move or not, or what's going to be the state of the equatorial Pacific, and then consequently the teleconnections. And this is how the connections show up in the northern latitudes. There's another result recently which showed if this part of the tropical Pacific is cooling, then much of North America tends to be warm. So again, the same teleconnection arguments that you cool this place, you warm the entire, because you're moving the rain bands north. So as a result, instead of getting rain, you get less rain, so it's warmer. So the basis for forecast. So this is what climate models exploit. The basis is what happens in the oceans has a bearing in terms of what happens to the climate in different parts of the globe, primarily coming through these changes in circulation. So the weather and the climate difference, you can think of it as weather is an initial value problem, climate is a boundary condition problem, boundary value problem. So what happens in over a coming climate depends on how the oceans are behaving, how they are evolving, what is the current state of the ocean. But if you want to know what's going to be tomorrow's weather, you've got to know exactly what the state of the system is today. So the initial condition of today is critical in determining tomorrow's weather. But if you want to know the statistics of the climate for the next coming season, then the state of the oceans is important. So that's where it's a distinction between the two, and that helps why you can predict statistics of the season, even though the predictions on the weather is no more than 7 to 10 days in winter time, and much less during summer, just like 1 or 2 days. So for the initial condition, you need a lot of observations, and that's what the efforts. So this sort of summarizes the need for probabilistic. So typically what happens is if you start from, say, today's weather and then you run forward, this is what you end up getting. After a certain point, you just get garbage because there's no skill in prediction. And this is the climatology, you can think of the average. So basically what you will say is after 5 days from now, the best forecaster is the average of the season, average of the month. That's what this envelope is. So if you are trying to predict using a single model, and then say I'm going to run it and just get one result, you can see that you could be off most of the time. So what do we?
Single model, you mean single initial.
Single initial value, a deterministic one run, and that is useless because you're not going to get information given the nature of the system. You're not going to be able to get and say the blue is the right, say that's the observed. This tells you the uncertainty and the time scale. So again, you can say all the way from weather to seasonal forecast to decade to climate change, and then you can see the uncertainty sort of increasing as you go out in time. So those are sort of the key areas where that's where the active research is going on. So what can we do? So again, as you notice, two things. One is we know these broad sort of features that dictate climate, seasonal climate, and we have fairly good understanding of these processes, but then how they write a signature on the weather and climate is uncertain, and that's where uncertainty capture is important, and that leads us to why we need all the statistical tools that we can get, in particular Bayesian methods. So there are two ways of doing these forecasts. One is dynamical, another one is statistical. Again, I just touched dynamical is build a model which got all the physics, everything, all the way from clouds and plants and soil and everything. And you've got to do this for the entire globe. Right? And they have that. They have few models in different centers of the world. Usually these run on grids. So you have a grid that says on each grid you're solving the Navier-Stokes equation at different levels in the atmosphere. And then you run it forward. And you have parameterization, you have tuning parameters for clouds, tuning parameters for various things, and so that's one area. So then you say, okay, I've got the best model representing the system, I take initial conditions, and then I run it forward. Problem is there's a lot of uncertainty in the initial conditions, uncertainty in the physics, and uncertainty in the spatial resolution. So these grids are usually 250 kilometers, or there are some that are much smaller. As you can imagine, if you are trying to make it smaller, computational demand goes up, and also you can't get ensembles, right? It takes 2 weeks to just run one ensemble, one member. So that is where statistics comes in. Yeah.
You said uncertain physics by that too?
Yeah. So for example, cloud. People have some idea of how clouds are formed. And they think, yeah, maybe I'll put in a parameter for the things I don't know. And that knowledge is constantly evolving. People have some idea of how evaporation happens from plants and roots. There are some basic physics that we know, but there's a lot that is unknown. So they stick in coefficients and parameters, the tuning parameters. So that's where I mean the uncertain physics or uncertainty in these models. So again, this is show the spatial. This is how currently the NOAA which is the agency in the US, they do their forecasting. So it's called the one step or one tier. So they have this integrated coupled ocean atmospheric model, as I just showed before, that operates on the entire globe. So they have several levels in the atmosphere, and then there's also ocean model. So it's all coupled, so it's all just one big entity along with land, and they run it forward. And that's what they use to do their forecast. So obviously they assimilate data into it. So they have observations of initial conditions that are assimilated in. They get the sea surface temperature, that is the sea surface temperature anomalies, and that then goes to the forecasters. It also produces the surface temperature, precipitation, and then the forecasters take all of this and make maps. And again, they don't simply take what comes out of this and run with it at a point and mention the need for statistical modeling there. So again, as you can see, this is, of course, the climate modelers love this. They don't like anything statistics. And sort of echo some of the discussion we've had yesterday. So it's sort of uniform and pervasive everywhere. So they just simply don't trust anything coming out of statistical models. And in fact, so much so, if you talk to some of them and say we need more data, they think model data is data. So, so you don't really win with them. But as you can see, it requires lots of data, and of course the thing is it's completely physical. So you're getting at everything from first principles, trying to put in the best knowledge that you have of all these various pieces. Here are some resources. As you can imagine, it's a massive undertaking, and I forgot to mention, National Center for Atmospheric Research in Boulder. They develop these models, and you can see armies of people working on this. So there's computational people, mathematical people to solve all these equations. So that's why you don't have very many of them in work. So there are very few. There's one more Australia as a model. So just a handful that have models that are of some work. I mean, there are other models, but these are sort of the real leading ones. ECMWF is very good for weather forecasting. That's what is used by aviation and everybody throughout. So again, to get a forecast or skillful information, then obviously you got to get ensembles, right? So you can't just take this complicated model and say, okay, I'll just run it once and I'm done. No, because we know you're just going to get some trajectory that might be or might not be, could be one among many of them. So the only way you can get somewhere is if you can run ensembles, which means you can either perturb the initial conditions and run, that's what they do, or you can run several models, right? So you can have the same initial condition, and I showed 3 of them before. So use the same initial condition, let 10 people run their models. So now you have 10 ensemble that each has different, coming from different information, different model, and then you can combine all of them, and that's where the Bayesian combination comes in. So I'm going to talk about the top 2 and 3. Same with climate change projections. The IPCC projections are made from several models, and they put all of them together, and then they combine. So right now, IPCC, they don't do any Bayesian combination, but again, as you can imagine, information is coming from multiple sources, each with its own sort of physics and biases, and the question is how do you put them all together to come up with a coherent ensemble or coherent information, and that is sort of a very hot area. This is what you get finally in terms of forecast, and this is produced by Columbia University IRA, where I used to work. And this uses the algorithm that I first developed in 2000 before I left, and I'll talk about that in the next talk. So essentially what they do here is they run 3 or 4 different models for the next season, starting from the current initial conditions. And once they have all of those, they then take the forecast from these different models, and it's combined in a Bayesian way. These are categorical, so what you're seeing is probabilistic forecast. So for example, here it says that there's a 45% chance of above normal, of below normal precipitation, 20% chance of above normal, 35% chance of normal precipitation. And these categories are tercile categories, so 1/3, 33rd, and 66th. So this is how you get information. And of course, this is the best you can produce. Yeah, they can give you fine categories, but there's no skill in those categories. Now, if you are a water manager sitting in one of these boxes, this information that you have, which is crude in space and time and probabilistic, you need to translate that into something, say, flow in the river, right? So that translation happens again through statistical models. And there are physical dynamical models as well, but then statistical models do the best, and you can come up with uncertainties and everything in that translation. So in the statistical approach, so that's what I told thus far is dynamical. So this is how they do in terms of models. In the statistical approach, it's functional estimation. It's very simple. Take the variable that you're interested in, go find all the predictors that you can find that is related to that, and simply fit a function. And typically this function is a linear function. If it's linear, then you're in the linear regression. Or you can fit nonlinear, which you have done using local polynomials or k-nearest neighbors and so forth. If it's multivariate, you can do principal components, orthogonalize, and then predict the orthogonal components. So you can do many of them, but at the core of everything is this regression framework. And what we have done is this variable y could be anything. It could be precipitation, it could be number of wet days, or probability of exceeding a certain threshold if you're only interested in extremes. So then the traditional linear regression sort of breaks apart. So that's where you go to the GLM. And the GLM, the way I look at it is it's sort of a step towards the Bayesian. So you're almost there with GLM. You just add a little bit priors and so forth, you end up with Bayesian. So I'll talk about that as well in the second talks with some applications. The multi-collinearity and best predictor selection that we know very well makes linear regression, and that's where the Bayesian hierarchical model helps out, because then you don't have to select which is the best subset. You put everybody in, and then each one comes in with its own distribution according to its importance, and that's where the hierarchical model comes in. So again, I'm going to talk about and show some examples in the second talks. This is sort of typically what is done. So what you're looking at here is the African rainfall, and you go find predictors that are related to, so this happens to be related to sea surface temperature in this region, and you plot, you see there's a relationship, and you fit a relationship and you use that for prediction. That's sort of very common, which is what is done, by the way, predicting the Indian monsoon. So they take the monsoon, find all predictors, and then they throw it in a linear regression. What you're seeing here, the problem with this approach is you're depending on prediction, correlations and relationships, and these relationships change. So for example, with the Indian monsoon, this is the correlation between the monsoon and the sea surface temperature here, and as you can see, it's pretty good. And when you get to the recent 2-3 decades, the correlation is getting close to 0. So if you are using this to fit your linear regression model to predict, by the time you get here, there's no scale. And a lot of the theory and modeling efforts have centered around capturing this relationship. And this was the time when Walker saw these good relationship with the monsoon that he reported. So that is something to keep in mind. But again, this is widely used because for one thing, climate data is ubiquitously available. You can just simply download stuff, do things on your own very easily, as opposed to running these complicated dynamical models. So that's sort of the methods for how forecasting is done in terms of climate, seasonal climate. The hydrology is feeding off of that. So once you have seasonal climate forecast, then you have to take that and bring it down to flow in the river, which is what we are interested in. So you are sitting here, there's a river, there's a reservoir, so you want to know how much flow is going to show up here. Well, that's dictated by what's the conditions that are set up at enough. And that comes from the climate model, and then you've got to translate it all the way down. So this translation, you can translate it via another dynamical model, or what I prefer is you can take these as boundary conditions and covariates and directly translate here using statistical models. And we have done this with pretty good success. So anyway, but that's how typically forecasts of hydrology are issued. And that is of interest to people, right? So people don't care about this. They want this. And you need to go through this, and there are both ways you can get to it. So this is just a quick sort of way of how forecast is issued. So in the US, they have all these river forecasting centers, and each river forecasting center takes these climate forecasts coming out of these models, and then they have their own translation tools to get there. And what they typically do here. So when they finally issue the forecast, it's actually something like this. So this is not an exaggeration. This is what actually happens. So they get forecasts from different sources, and then the water managers or the forecaster in the forecasting office says, this year looks like 1983. I think we're going to get more snow. Okay, so put it in the crystal ball and massage it, and then they come up with a forecast. And this is where, again, model combination can be very helpful, and I'm going to show examples when I get to talks 2 and 3. Okay, so let's see what I can. So going to simulation. This is not something that's usually a problem that you see in many fields. Meteorological observations are limited in time. So if you at most have maybe 30 years of daily rainfall, or 40 years of stream flow. If you want to make decisions here, you want to decide what should be the size of a reservoir and planning, or what should be the size of water treatment plant, then you are doing risk-based decision making. So you want to know what's the risk of getting certain events that are impactful for my infrastructure that I need to take into account. But if your 30-year record does not have those kind of events, then you're not going to be generating the risk appropriately. So the only way that you can get around is to fit a model and simulate scenarios. And that's where simulation comes in, or stochastic simulation. So one of the most important simulation is the weather generation. So which is you have limited daily data, and then you need to generate lots of sequences of daily weather for use in crop management or economic model, insurance models. And that is an area that I've worked a lot on. And there are several methods, and one of the GLM-based approaches, and more recently we've been working on the latent Gaussian process. And this is something I'll talk about also in my second talk. So this is just an output from one of the recent work that we did using latent Gaussian process. So if you have observations in space, this is Iowa, and this is a region in Argentina. So you have daily weather over these locations, and as a crop model or agriculture planning, you want to get daily weather over the entire region. So you take observations if sparsely located in space, and you want to generate continuous observations in space like this, and this translation happens through latent Gaussian processes. And you can do this for each day, so this is a representation of a simulation. So you can do this for precipitation, you can do this for temperature, and once you generate all of those, they can then drive your crop model or water model or various other models which require daily weather as inputs can then be passed through. And stop with this one. So this is just one slide. So the last bit I want to talk about is the extreme value analysis, and this is also again very uniquely water resources problem, which is trying to look at the floods. Right? So this is a classic example, and there's been a National Academy study on this. This is American River in near Sacramento. So this is the annual maximum. So you're looking at the annual maximum flow in the river. So you have all the daily flow. This is the block maximum. So it tends to be GEV, generalized extreme value. But this is what you have, and this is when they built the dam. They said, well, there's a lot of flooding happening. And they used data here, and they said, okay, it's 80,000 units, and then okay, let's build a dam. And they put the dam, thinking that it's going to protect them against a 100-year flood. Then look what happened after that. So this maximum has been exceeded 6 times. And now the city is not even protected against a 20-year flood. So what is happening here is the extremes are changing to this non-stationarity. And it turns out that that non-stationarity is directly linked to more El Nino events happening in the recent decades. So in this part of the century, there were very few of those events that I was mentioning. The answer, somebody asked how frequently it changes. Well, it can go decades with very little activity. And if you happen to be in that phase and say, well, everything is fine, I'm just going to use that and make my decisions, this is what you end up afterwards. So again, there are ways by which you can use extreme value theory to incorporate knowledge of climate information. And and that's something I'll touch upon later. But anyway, I'll stop there. So there are methods, Bayesian methods, as I pointed out, model averaging, hierarchical modeling. Those are sort of the two main Bayesian methods that we have used quite a bit, and I'll show in the next two talks sort of various applications, specific applications of these. So, stop.
Questions?
Yeah, so this is sort of more of a overall high-level question, which is, have there been attempts to bridge that gap between the different levels of forecasting, where you have a unified model where the higher level sort of forecasts are being used to make predictions at the lower level more accurate? For example, the climate level forecasting models are being used for the weather prediction models, so having a multi-scale sort of prediction.
Yes, so what NOAA is trying to do is to have a single model, very high resolution. So you use that to do your weather prediction, and then you use the same model to do, I forget the term for it, but it's bridging across scales.
Right.
So, but the thing is, processes that happen at those decadal time scale or 100-year time scale are quite different from the weather time scale. And also resolution, for example, for weather you need very high resolution to resolve the thunderstorm activities and so forth. But whereas if you want to know what's going to happen 100 years under climate change, you can get away with not having that high resolution because you want to get some broad processes and you're mostly interested in what is the distribution of temperature relative to today. Whereas the weather, you really want that thunderstorm because if you don't get it, then people are angry or it's not much use. But yes, that's sort of where all this is headed towards in terms of the modeling part of it.
So related to that, are there any sort of adaptive grid methods?
Yes, so NCART does that. So it's called, there's a term for it, but it's adaptive grid. So what they do is, in fact, they also have adaptive grid over specific regions. For example, I know the place where I work a lot is on the Colorado River. The headwaters of the Colorado River are in the high mountains. So that's where there is a fine mesh to resolve rainfall, snow, and so forth, the elevation effects. And then as you get away, the grids become larger. So there's work going on in that area to do the adaptive.
Right. Let's thank Balaji.
Thank you very much.